Our next talk discusses pattern matching in the Glasgow Haskell compiler. It is based on work by Sebastian Groff, Simon Peyton-Jones, and Ryan Scott. The talk will be presented by Sebastian.
Hi, I'm Sebastian and I'm here to talk to you about pattern match coverage checking. In case you're wondering how this problem hasn't been solved like 40 years ago, well, lower your guard and hold back on your judgment just for a few more minutes. Let's start with a quick recap about pattern match warnings. This incomplete definition of is just in Haskell here will crash when called with nothing, because it lacks a covering clause. Now, runtime crashes are annoying, especially for such an obvious oversight. So the compiler should, and indeed in the case of GHC it does, warn about it. I'll talk about how GHC figures out these missing cases. Apart from such missing equations like nothing here, compilers can also find redundant equations like the third one here. In fact, compilers have been able to produce these kinds of warnings for a long time, so you might think there's nothing new to find here. And I thought so too, before I picked up maintenance of GHC's pattern match checker as a side project about a year ago. As of recently, there are still 28 open tickets for the pattern match checker, most of them related to performance and incorrect handling of some subtle interaction of source syntax features. So how exactly can something that looks so simple give us so many headaches? Let's start with a little warm-up exercise. Is this function exhaustive? Well, that's a pretty suggestive question, and since this isn't a live talk, I won't be waiting for you. The answer is no, and these are the values that it failed to cover. There are only 4 pattern matches, but 16 different combinations of arguments to consider. Clearly, a scalable automated checker needs to know when and how to bail out of this exponential behavior. Now, Haskell is lazy, but not total. That also reflects in its pattern matching semantics. Take this function here as an example. It might be tempting to think that the second equation is redundant, but in fact it isn't. Deleting equation 2 would alter the semantics of the function from crashing to returning 3 in this call here, so not redundant. But on the other hand, we can never return to, which definitely smells like a bug worth reporting to the user. We say that the equation has an inaccessible right-hand side. Of course, when we call a clause redundant, that always implies its right-hand side is inaccessible. Lazy but not total also means that we have bottom inhabiting every data type. That includes the data type void, which doesn't have any data constructors, so bottom is its only inhabitant. These examples here introduce bindings of type void by resorting to divergence and runtime errors. F here matches on them in a lazy wildcard match, and it's just a regular exhaustive function definition. Now that we have void, we can combine it with strict fields. Here is a strict maybe data type, as you can tell by the strictness annotation on sjust's field here. Whenever sjust is constructed, its field needs to be evaluated first. The function f here matches on smaybe of void. Question: is the second clause of f redundant or not? We can answer this systematically by enumerating the inhabitants of smaybe void and see which equations of f match them. The only 2 inhabitants are bottom and snothing. Sjust of bottom is not an inhabitant because of the strict field. The first equation of f diverges on bottom and matches on nothing. So yes, redundant. There is no value possibly reaching the second equation. Guards are another very basic pattern language feature of Haskell. Does sign have any redundant clauses? In general, it's hard to tell without knowing the definition of less than, eq, and so on. Also, we'd quickly become undecidable if we just reason about every function we know the definition of. So, apparently guards are quite rich semantically speaking. Here you can see how it's even possible to do pattern matching with pattern guards. And get here even mixes both structural pattern matching and pattern guards. This definition is exhaustive and the compiler should not flag it as non-exhaustive. I hope it has become clearer that there are a lot of surface language features that the pattern match checker has to cope with efficiently. Also, many of these features interact with each other. I won't have time to talk about the ones in parentheses, like long distance information, so please do ask questions afterwards and read the paper if you're interested. The status quo in GHC was based on a 2015 ICFP paper that handles most of the language features in the previous list, including GADTs and type level information in particular. But having been battle tested over the last couple of years, the implementation revealed shortcomings in being too buggy and slow. Also, it was pretty complicated. In trying to improve on what we had, we iterated a couple of times and came out with a new approach we called Lower Your Guards. As the name suggests, we abandon all structural pattern matching, like in F here, and desugar function definitions into guard trees. Then we do coverage checking on these guard trees, which is split in two simple functions A and U. A returns an annotated tree, decorated with refinement types that capture redundancy and inaccessibility information. If you want to know more about this part, I encourage you to read the paper. U computes the set of values that weren't covered by any clause as a refinement type theta. And then all we have to do is report the inhabitants of theta as uncovered patterns of the definition. Let's desugar this fancy example function. Green indicates source syntax. You can see that fancy makes use of constructor patterns and even two language extensions, a bang pattern that forces the matched thing, and a view pattern that applies the matched thing to G and matches the result against true. In yellow, you see fancy's desugaring to guard trees. Here is the syntax definition for reference. Let's focus on tree syntax first. There's one branch in the guard tree for each clause in the function definition, modeling fall-through semantics. There are also a bunch of guards on each branch, and each branch ends in an ordinal that identifies a particular clause in the original program. Looking at guards, we can see that nested pattern matching was completely decomposed into multiple flat pattern guards, like on just here. Pattern guards are considered lazy, and evaluation is forced by bang guards, such as on x1 here, which stands for the first argument. Pattern guards can only match on variables and only one level deep at a time. We give names to more complex expression, like this function application, with a let binding, which also allows us to desugar the view pattern here, for example. Desugaring also introduces a few administrative lets that fix up naming differences, like the one binding x's to the temporary t2 here. We found similar desugarings for all the pattern match syntax of modern Haskell. Also note that this desugaring is for coverage checking only. There is no code generation involved. Alright, next up, characterizing the set of uncovered values that we can report uncovered patterns for. We compute the set by gradually refining the set of possible values as a fraction of them falls through from one clause to the next. How do we represent such a set with possibly infinitely many values? We picked refinement types for the job. Here are a few example refinement types in blue, as well as the sets they denote in orange. Cross is the unsatisfiable refinement predicate, so there are no inhabitants. Checkmark is the trivially satisfiable refinement predicate, which means we have all the inhabitants of bool. This is the type of unlifted booleans, and this one also rules out false. This last one here shows what's unusual about our refinement types. It has a pattern guard on MX that brings justs field X into scope, which then scopes over the conjunct to the right of the pattern guard. For some reasonably simple end-to-end example, consider this source program. It will desugar to this guard tree, which in turn we can compute the uncovered set for. Note that the resulting refinement type has a disjunction in its predicate, because we can fall through from this clause here in two different ways. First, the match on just could have failed, and even if the match on just succeeded, the match on true could have failed. Question now, how do we do this in general? With a function like this, u computes the subset of theta whose values do not match the guard tree T. When we reach the right-hand side, every incoming value is covered, so we return the empty refinement type. Branches model fall-through semantics. Only values that fall through the first branch can fall through the second branch. A bang guard on X adds the constraint that X can be bottom to the incoming values of the subtree. Likewise for let bindings. A pattern guard matching against constructor K will fall through when X is not K. Also, everything not covered by the subtree is uncovered, so we adjoin the two refinement types. And that's all there is to coverage checking. The next step is to generate inhabitants of the refinement type falling out at the bottom. These are the uncovered clauses which we want to report to the user. If it's empty, then the pattern match was exhaustive. For our particular running example, the inhabitants are easy to find. Just true and just false, which are already in a suitable form to be presented to the user. Algorithmically, we could use Liquid Haskell's embedding of refinement types or an SMT solver directly to generate inhabitants. But we didn't do that because reflecting GHC's type constraint solver into SMT logic is quite an undertaking. And we think that FFI calls and serialization of facts incur too much overhead. So we bit the bullet and just wrote our own ad hoc generator function. You can read more about its implementation and its completeness properties in the paper. Now, for an uncovered set coming from an obviously exhaustive definition, like H here, we find that we can produce any inhabitants. So, no values to represent, hence no warnings to emit. H is found to be exhaustive. In conclusion, we came up with what we find to be quite a nice solution to pattern match coverage checking. It took us many iterations to get there, but in the end it paid off. The end result is at the same time simpler to think about, simpler to implement, and executes much faster. The fact that we invented it for a lazy language shouldn't stop you from lowering your guards in strict or even mostly imperative languages. Just write your own desugaring function. And if you're in the process of writing a coverage checker and don't want to make the same mistakes, I can only encourage you to read the paper. Lots of more stories to be told about language extensions and efficiency concerns. Alright, that's it. Thank you for listening.
Thank you, Sebastian. If you are watching this talk live, be sure to join the Q&A session with the author if it is available in your time zone.